Hi Guy, I'm Laurie from AI Elephant.
Hi guys, I'm Leo.
Hello everyone, and welcome to the show. Leo, we talk so much about AI, but it feels like there is one promise that has never been fulfilled, you know? The C-3PO from Star Wars, the humanoid robot that can bring us tea and do everything. Where are they?
Right, now that you mention it, we've been waiting for decades, and it seems like robots are still just vacuuming floors and assembling cars. Did we just imagine the whole robot thing wrong from the start?
It is very possible. Maybe the robot of the future isn't humanoid at all. Maybe it will exist in forms we never expected worn on our bodies, or even inside our bodies. We always expect a general-purpose robot, but Professor Monroe Kennedy from Stanford offers a new perspective. The future of robotics should be defined by society's needs. For example, the world's aging population.
The aging population, I get that. Many elderly people are cognitively sharp, but their mobility, especially their hands, isn't what it used to be. Even picking up a pill bottle is difficult.
Exactly. They want to live on their own, but there isn't enough human power to help with all these tiny, dexterous tasks. If robots could handle these small things, it would massively improve their quality of life.
So it doesn't have to be a person? It could just be a very dexterous arm or an assistive device?
Precisely. Professor Kennedy also mentioned manufacturing. For instance, assembling a pen in the US is actually impossible right now because of labor costs. But if robots could handle that complex assembly, it could onshore the assembly and reshape the industry.
I get it. We don't need a replica of a human, we need a tool that solves a specific task. So, what about agriculture? Picking fruit seems doable, right?
That leads perfectly to the next critical point. It is not just if the robot can grab something, but how it grabs it. Kennedy's lab, the ARM lab, studies this dexterous manipulation. They have an example of a robot picking strawberries. The point isn't just to pick it, it is to analyze the degree of damage done to the fruit after repeated picks.
Wow, that is tough! I bruise my own strawberries just by looking at them. How does a robot even know if it is being heavy-handed?
This is the key, tactile sensing. They've developed a dense tack sensor that costs less than $40. The robot has to be able to feel how to be gentle.
We desperately need this. I always feel like current robots are so clumsy. If I asked one to fold my clothes, I'd be genuinely afraid it would shred my cashmere sweater.
So, touch is the critical step for robots to safely enter our homes and handle our things. They have to learn to be gentle, not just follow commands. Beyond home service, Kennedy also mentioned wearable systems, like those for amputees or people who have lost mobility.
I've seen some of those, like the mechanical arms in movies, but what is the biggest hurdle? How does the robot know what I want to do? Is it brain control?
Not entirely. The core challenge is extracting the user's intent. For example, by using eye tracking or by picking up tiny electromyography muscle signals. The system doesn't need you to control every single joint. It just needs to understand the small cues you provide and then extrapolate how to be the best assistant for you. Everything we've discussed so far has been mostly in the realm of rigid robots. But another professor, Renee Zhao, her research is, well, it is disruptive. She focuses on soft, intelligent materials.
Soft? Like Jell-O.
Laughs almost, but smarter. A lot of her inspiration is bio-inspired, like an earthworm crawling or an octopus arm.
The octopus. I heard that 90% of an octopus' S-brain is in its arms.
You've hit the key point. Rigid robots rely on motors to create degrees of freedom. A soft robot's movement comes from the deformation of the material itself. Every single material point in its body can deform.
That sounds like too much freedom. How do you even control that?
This is Professor Zhao's core mental model, separating the control unit from the body, or decoupling. For example, she uses a magnetic field as the external driving force. The robot body itself can just be an inactive origami structure, and the control comes from manipulating the external magnetic field. This decoupled soft robotics has an incredibly important application: endovascular robotic surgery.
Inside the brain? You mean for a stroke?
Yes. Currently, mechanical thrombectomy clot removal for strokes is often ineffective. The catheters are too stiff to navigate the highly tortuous blood vessels in the brain.
The vessels are so fragile, and it all relies on the doctor's feel. Only the most elite surgeons must be able to do that.
That is right. Stanford only has 4 such doctors, and it takes over a decade to train them. But Professor Zhao's team developed a spinner thrombectomy device. It is about 1 millimeter in diameter.
1 millimeter? How does it work?
It is the soft robot we just talked about. It is driven by an external magnetic field spinning inside the vessel. It acts like a tiny drill, densifying the clot and reducing its volume by over 95%, which then allows it to be removed.
My God, that is not just technology, that is life-saving. It means that in the future, a remote hospital could use robotic assistance to perform this kind of top-tier surgery.
But whether it is Professor Kennedy's home robots or assistive prosthetics, they both mentioned one common, massive hurdle: the sense of touch.
Touch! Didn't we just say Kennedy's lab is making sensors? Why is it still the biggest hurdle?
Because touch is far more complex than we realize. Kennedy gave an example. A person with numb fingers, even while staring directly at a matchbox, will take 3 to 4 times longer to light a match. Touch is a vital part of our internal control policy.
I get that. It is like trying to use your house key while wearing thick winter gloves. You can see the keyhole, but you just can't feel it.
Exactly. And the human finger can sense at least 4 modalities of touch: shape, normal force squeezing, 2 kinds of sliding frictions, and rotating torsion.
To replicate all 4 of those and then communicate them back to the wearer, that seems impossible. Our arm, for example, just doesn't have that density of nerves.
It is a huge sensory conveyance challenge. Some researchers are trying vibrating motors or using AR headsets to show the user a visual analog, a force profile.
But that sounds exhausting, having to watch my sense of touch.
Which leads to a potential solution: offloading perception. The robot doesn't have to tell you all the high-resolution tactile information it is feeling.
How so?
Take a complex task like untying a tiny knot. The human just needs to communicate the intent: I want this untied. The robot then uses its own high-density touch and control its innate ability to handle the most complex part of the task all by itself. We've been saying AI a lot, but Professor Kennedy specifically warns against the universal hammer mindset. Just because you have the AI hammer doesn't mean every problem is a nail.
Oh, so if you don't use AI, what do you use?
Analytical solutions. The essence of AI is pattern finding. But if a problem has a clean, fast analytical solution, you must use that first.
So when do you use AI?
When a space is too complex for a clean analytical representation. For example, learning from humans. The robot observes a surgeon's data. When it encounters a similar scenario, the decision it makes should fall within the distribution of the decisions the human doctor would have made. This brings us to the mental models that both professors are really giving us, which go beyond the technology itself. We just mentioned Kennedy's analytical data, dual track. Professor Zhao's model is control and body decoupling.
The one using magnetic fields to control the soft robot from the outside.
Right. This decoupling gives the robot a biological compliance. In a confined environment like the human body, it can passively deform to adapt rather than breaking.
It gains that infinite degrees of freedom, just like the octopus.
And this raises a much deeper question. You mentioned earlier that 90% of an octopus's neurons are in its arms. Zhao suggests this implies a kind of thinking deformation.
Thinking deformation! As in, thought can be directly mapped to motion!
Yes, it suggests a future where robots are no longer a brain giving orders to limbs, but are instead created with integrated think and motion. So, to go back to our original question, Maybe the robots we've been waiting for never showed up because we were trapped by the humanoid concept.
We were stuck, trying to build a replica of us.
But today we saw that the future of robotics might be, 1, defined by social need. They are the dexterous hands solving the problems of aging and manufacturing. 2, soft and bio-inspired. They go inside our blood vessels, thinking and moving like an octopus. And 3, centered on touch and intent. They aren't cold machines, but extensions of our own bodies and capabilities.
From the rigid C-3PO to compliant, thinking matter, that is a massive leap in imagination. Thanks for listening!